target, airborne target. Um, and this is a typical communication systems example where you have a transmitter and a receiver, but the thing is that the transmitter and the receiver both fall, or both are placed at the same location, rather than in a typical communication system where you have a mobile phone, transmitter is somewhere else and the receiver is sitting maybe in Australia or New Zealand or somewhere else. In radars, the transmitter and the receiver are at the same place, and we assume that the wave transmitted by a radar is never going to come back. But if there is a target, the wave will reflect back and will come back to the radar itself and received by the receiver. And what happens is that continuously the computer of the radar computes correlation between the transmitted signal and the received signal. Obviously, the received signal will be low in power, but the shape of that signal will be very similar to the transmitted signal if it is reflected back. And there will be some delay as well, because the wave has its own speed. It goes and comes back. It cannot happen that the signal comes back at the same time. So we look at the degree of similarity and the lag, or the distance, or the time it takes for a wave to go and come back. So if the signal comes back with a very short span of time, it means that the target is very close, is very nearby. And if it takes a rather long period of time for the signal to come back, it shows that the target is at some distance. So using the wave speed and using the sampling frequency of the signals, we can easily find out the distance, and that's the basic principle of the radar using correlation. In fact, we can take on a simple example to see how it works. So for example, a radar is transmitting a signal at 100 megahertz sampling rate. So every second the radar is transmitting 100 into 10 raised to power 6 samples in 1 second, and the speed of that transmitting wave is 1 into 10 raised to power 8 meters per second. So this we know from the data. And for example, we get the reflection of the transmitted signal. We get a spike of the correlation, high correlation, but the lag value is 3000 samples. So it means that when the signal went, it took 3000 samples equivalent time to come back at the receiver. So now we have to calculate the distance between the target and the radar. Remember that the wave travels twice the distance between the target and the radar. So once it goes to the radar target, and then it comes back to the radar. So the distance traveled by the wave is actually 2 times that of the distance between the target and the radar. But let's now try to visualize this problem. So this is the data we have. Fs is 100 megahertz. So every second we are releasing 100 into 10 raised to the power 6 samples. The velocity of the wave is this, 1 into 10 raised to the power 8, and the lag is 3000 samples. And this is the same data transmitted, reflected on the figure to better understand the scenario. Now the question is, can we find out the time it takes for the signal to come back? Because if we find out the time it takes, 1 second, 2 seconds, whatever, then we know the speed of the wave, and then we can compute the distance which is actually required. We know that every second 100 mega or 100 into 10 raised to the power 6 samples are sent by this radar, and in 3000 samples we have got the signal back. So we have to basically find out the equivalent time of the 3000 samples. So you can focus here. It's very simple. That the sampling time of the radar is 1 over Fs, which is 1 over 100 into 10 raised to the power 6, gives us 1 into 10 raised to the power minus 8 seconds per sample. So one sample is released every 1 into 10 raised to the power minus 8 seconds. So if a signal is coming back in 3000 samples, then it means then 3000 multiplied by 1 into 10 to the power minus 8 is equal to 3 into 10 to the power minus 5 seconds. So now we know the time that it takes 3 into 10 to the power minus 5 seconds for the wave to travel the entire distance. That is to go from the transmitter to the target and then coming back to the receiver signal. It is actually taking 3 into 10 to the power minus 5 seconds duration. So previously we knew only the number of samples. Now we have converted the sample into seconds. Now we know the time, exact time it took for the signal to go and come back. Now can we find the distance the signal traveled using the velocity of the wave? So it's very simple. We know the distance is equal to velocity into time. So it is 1 into 10 to the power 8 is the speed of the wave, and it took 3 into 10 to the power minus 5 seconds to travel the distance. So you multiply both, the distance come out to be 3000 meters. So essentially the wave traveled 3 kilometers, which is twice the distance between radar and target. So the distance between radar and target will therefore be 1.5 kilometers. So you can play around with these numbers and try for yourself how this works. The radars today have become very sophisticated, but all computations are based on this very simple calculation. Whether it is ultrasound or the underwater mapping devices or radars or satellite mapping, all use correlation as a measure of say degree of similarity, and this is what our topic of discussion was in today's video. So to summarize, we looked at the cross correlation, which is correlation between two signals X and Y, and we looked at that if we correlate signal X with Y or Y with X, both provides us the same answer, except that the signals are the folded versions of each other. Then we looked at autocorrelation, which is essentially the correlation of a signal with itself. Then we looked at the normalized correlation, which essentially allows us to make sense of the numbers of correlation, which is between -1 and 1. We have seen that the 1 is the maximum value, -1 is the again maximum value, but in the inverted sense, like happens in a sine wave and its inverted version. And 0 is a dissimilar signal, which happens like, for example, if you correlate a sine wave with a cosine wave, then the correlation is 0. And correlation in the vector sense is very similar to the dot product. So if the angle between two vectors is 0, then we get a highest projection. And if we have two vectors with 90-degree phase shift between them, then they are called orthogonal signals, and their dot product is 0, and the correlation is also 0. And we looked at the calculations of correlation, normalized correlation, and we looked at an application example of the radar. So this is what we covered in today's video. And the reading section is 2.6 of your textbook. And with that, we complete today's lecture. Thank you.